Okay, parametric functions. Okay, so to this point in your mathematical career, you've dealt with y equals a function of x, mostly. Mostly, that's what you're used to. That x is like the input quantity, and you put x through some kind of formula or rule, and that generates a corresponding output quantity, and conventionally we call that the y value. Okay? And so we have notation like f of 4, which allows us to denote what the output of the function is when the input is 4, right? So this is the output of the function when the input is 4. It's not just a long version of y, right? It's not just a long version of y. It tells us more. It tells us what the y value is when x is 4. Okay, so that's function notation. Okay, so now we're going to look at another kind of function. Parametric functions. Parametric functions are of the form where both x and y are each individually a function of t. Both x and y are each individually a function of t. So here's an example. X equals t plus 2, and y equals 1/2 t cubed. So now as t varies, x varies, and as t varies, y varies, and that creates your set of ordered pairs. Instead of y always being generated by the current value of x directly. Okay, so for example, so this is just the idea of it, but you're rarely going to be building tables like this, but you should understand what's going on here. So when, for instance, when t equals 1, what is x? 3. And y is 1/2. So when t equals 1, we get the ordered pair 3, 1/2. And we still plot that point in the xy plane. So t is in the background, right, of the graph. In terms of looking at the displayed graph, you don't see t. You still see just x and y, but those x and y values are being generated by this kind of invisible t. Okay? So when t equals -1, what ordered pair do we get? 1, -1/2. One more, when t equals 3, x equals 5, y equals 27/2. Okay, so let's actually, this is this graph, so we should see the point 3, 1/2. There it is. When t equals -1, we get 1, -1/2. And then when t was 3, 5 off the screen. So let's do 2. What is, when t equals 2, what do we got? 4, 4, 4? What? I thought this was the graph of this. Oh, t equals 2, right? So 4, 4. So 4, 4. Okay, so for increasing t, then, we have something new here that we didn't have before. For increasing t, the points plot in a direction. So the direction of the curve. Okay? So for increasing t, you get a direction to the curve, right? So what's the direction for this one? Is it down and to the left or up and to the right? This is for t equals -1 here. And this was t equals 1, gave us that point. And then t equals 2 gave us this point up here. Therefore, direction is up and to the right, right? So the direction of this curve is this way. So we're saying how are the points, how do they emerge as t increases? That's the direction of the curve. Okay, t is called, so the parametric function is because t is called the parameter. So there's this parameter that's hiding in the background. As that changes, x and y are functions of that parameter. And for a given t, you get a point, and then as t changes, you get a set of points. And that set of points creates a graph in the xy plane. Okay, so for this one, so I gave you the function parametrically, but it can be written as a function of x, in the old school way, right? The way you're used to. Okay, writing it in terms of x, as a function of x. How can we do that? Well, so this kind of looks like that, right? We have y equals 1/2 t cubed, but that's y in terms of t. So how can we get then y in terms of, it's like we're almost there. We just need this to be in terms of x instead of t. How can we do it? So you're so smart. You're so smart. Okay, so t equals what? X minus 2. So if t equals x minus 2, then y equals 1/2 x minus 2 cubed. Which is the same. So what's the same about this? It's the same set of points. You get the same set of points, but now the parameter's gone. That generates the same set of points as before. Okay, so there it is. Okay, so that's the basics, right? So the basics. Given different values of t, it generates ordered pairs x and y. For increasing t, you get a direction to those points being plotted out.
So with the y function, it wouldn't have a direction anymore, right?
That's right. Unless you talk about, like, normally x, right? So you think about x increasing, and then you can talk about this graph is an increase, y increases as x increases. Okay, but we don't talk about a direction of the curve. Okay, but we do talk about y increasing or decreasing for increasing x. For this function, y increases as x increases. right, what do we want next here? Parametric curves. I don't want that. I want the linear one. Okay, so here's some things you can get. Like here's some different versions of what you can get here. But so like with y as a function of x, we could never get this, right? We could never get this. This is not clearly not a function of x. But when you introduce a parameter and you do x and y separately as a function of a parameter, you can get all kinds of crazy curves, okay, that you couldn't get before. Yeah, that's all one curve. So what do I want? No, I want linear parametric derivative. Okay, here's one. Okay, x equals 8t minus 3. And y equals minus 6t minus 2. Okay, so practice, write y as a function of x. So first we get to what t equals. What does t equal? Should have gotten x plus 3 all over 8. And so then you can write y as? Okay, and if we simplify that, so let's get that into, if we simplify that like as y equals mx plus b, we're going to have negative 6/8 x, that negative 3/4 x. Okay, and then I'm going to have negative 3/4 times 3 minus 2. So if you do all the math, you get negative 17/4. You can do it later. That's 7th grade. Okay, so it's negative 6 times 3/8 and then minus 2. So that whole constant term. Okay, so now suppose we started with this. So then that's this line, right? So this set of parametric equations graphs this set of points, which is what we formally, or what we're more commonly known as this line right there. So if you had started with this, we didn't know anything about this over here. How could we write that in parametric form? So suppose we started with this function of this, or this equation of this line, and we wanted to write it in parametric form. what could we do? So there's seemingly nothing about this that's 8t minus 3 for x and negative 16 minus 2. So it seems unrelated, right? So what could we do to this to set up to write x equals something and y equals something? There's something really easy we can do to make this work.
Find what order pairs are and try to find relation.
That's hard. So it's a lot easier. It's not that we're trying to get this. Forget about this. We're just trying somehow to write x as a function of t and y as a function of t that would give us this equation. Yeah?
You just put x is equal to t, and then, or
Yep.
x is equal to t plus or minus something, and then plug that x equals t function into the y function.
I liked your first suggestion. We'll just say x equals t. And if x equals t, then what is y as a function of t? Okay? Now, this doesn't work. This isn't the best thing to do in every situation, okay? But this, in some situations, it's appropriate, like this one, okay? So let's just test it here. So if t equals 1, what order pair do we get? So here's our original. If t equals 1, what do we get? 5, comma, negative 8. And so now if t equals 1 down here, what do we get? 1, comma, negative 3/4 minus 17/4 is negative 20/4. Or? Is it right? Did we make a mistake?
No, it's on the graph still.
It's on the graph still. What's going on here? What happened? This is a key point about parametric functions. What happened? If I plug t equals 1 into my original, I get the 0.5, negative 8. I found y as a function of x correctly, and I made a new set of parametric equations from that, and now if t equals 1 for that one, I get 1, negative 5.
It's a direction.
Okay, so here I'm actually showing both, okay? I've got, is that? Yeah, that's what I've got.
So does it still make the same line?
Okay, go ahead. It makes the same line, but?
I guess it just starts from somewhere else.
Right, so it's making the exact same line. It's the same set of points. It just does it differently for different values of t. Okay, so the blue one is, so here I'm changing t slowly, and the blue one is this one that we came up with here. And then the red one is our original. Let me put this in red so you know. What point was it? 5, negative 8?
Yeah.
Okay, so I'm gradually changing t down there at the bottom of the screen, and I'm plotting the current value of the point for each set of parametric equations. So you see that they're tracing out the same set of points. It's just you're going to get different points for different values of t. You won't get the same point for the same value of t, but you end up getting all the same points in the end. Okay? So is it the same function or is it a different function? Is it the same function or a different function?
Different functions and parameters.
They are different functions that generate the same set of points. They're different functions that generate the same set of points. Just by plugging in t equals 1 to that first one, I got 5, negative 8. I plug it into the second one, I get 1, negative 5. That's a different set of functions. But when you let t vary for both functions, you end up with the same set of coordinated pairs x, y. Okay, which brings us to Rate of change. How can I talk about, say, this red function here? Rate of change. What would represent rate of change in this red function? What could I do? I've got x equals 8t minus 3 and y equals minus 6t minus 2. What could I do? Rate of change is what?
Y over the change
Can I do dx? Oh, I thought I did this already. Can I do dx? Dx what? Dx dt. What is it? What is dx dt for the red function? 8. Dx dt is 8. What does it mean? So what does that number 8 mean? What's changing in a constant rate of 8 seconds? So given a change in t, the change in x is 8 times as much as whatever change in t I have, right? So whatever change in t I have, this is, remember, dy equals k dx, right? So but now this is dx equals 8 dt. So for any given change in t, my dx changes 8 times as much. And what about dy? dy dt is? For any given change in t, how does y change? Negative 6 times that change in t. Now let's do, for the blue function, let's do dx dt and dy dt. dx dt is? 1. dy dt is? Negative 3/4. Look at what's happening as I increase t the same for both functions. How is the blue graph being traced out? For a change in t, I get the same change in x. And I get 3/4 of a decrease of that change in y. But then for the red graph, for a change in x, I get a change of x of 8. And for a change of t, I get a change of y of negative 6. So how do you see that playing out there in that animation? Every time t changes by 1, that blue dot increases its x by 1 and goes down less than 1 in y. But every time t increases by 1, x increases by 8 and goes down by 6. So that's exactly what we're seeing here in the graph. Yeah.
Wait, so dx over dt for the first function is 8.
Right.
But
So watch. I'm going to change. If I change. Okay, so I'm going to change at t from -1 to 0. So when I change t from -1 to 0, look how much the red one changes and how much the blue one changes. Here's -1. There's 0. So the red point just changed x by 8 and went over 8 and down 6. And what did the blue point do? It went over 1 and down 3/4. If I do it again, I go from 0 to 1. Here's t going from 0 to 1. Ready? T is 0. T is 1. We saw the red graph sweep out 8 and -6, and the blue graph only swept out 1 and -3/4 for that change of t of 1. And that's what those numbers are saying. And that's what you're seeing. Okay, so not only do we get different ordered pairs for the same value of the parameter, but the way in which the points are swept out is totally different, right? At a totally different rate. So just underscoring that these are two very different functions. But what's the same about them is they give you the same set of points. Okay, that was better than you think. Let's look at that. Any questions on that? So what is this one? We need this one. Parametric curves. Okay, here's that one that you're oohing and eyeing over. So I've got this as x equals 2 pi some coefficient, or sine, 2 sine some coefficient t, cosine 6 pi t. And if I change that coefficient in x is when I get these different variations. So these are all different functions. I'm changing this value n right here. So let's do this one. So this function is x equals, so n is 6, so x equals 2 sine 6 pi t, and y equals cosine 6 pi t. So when you use parametric equations and use sine and cosine with x and y, then you get ellipses and circles, okay? So this one in particular is an ellipse. So can we write as an equation of x and y? So this is not where you're going to solve x for t and plug it into y, because what's going to happen if you try to solve x for t? What are you going to get? X over 2, yeah, and then arc sine, right? We're going to take the arc sine, we're going to plug it into y. This is not the way to go. This is not the way to go. Don't do that. You don't want cosine of something arc sine. So we have a different strategy for this. We need something where we can eliminate t. We need something to do with sine and cosine where we can eliminate t. Does anybody remember your trig? Well, tangent, so we could divide and get tangent, but it's still tangent of t. So we need something that combines sine and cosine and gets rid of the t. What square? Okay. So you're right about sine squaring. What do we have with cosine squared and sine squared? Right. So notice that if I can get a sine squared of an angle plus cosine squared of the same angle, that equals? And there's no theta there, right? No theta. That's what we want. So notice we've got the same angle, 6 pi t. The argument for sine has to be the same for this to work. What's going into sine has to be the same angle measure. And we've got it, 6 pi t and 6 pi t. So if x over 2 equals sine of something, in this case 6 pi t, and then y equals now I can, if I squared sine and squared cosine and added them together, it would equal what? 1. Well, what is sine squared? X over 2 squared. What is cosine squared? Y squared. So basically we're doing sine squared, 6 pi t, plus cosine squared 6 pi t, and we know that equals 1. But what is sine squared of 6 pi t? X over 2 squared. And what's cosine squared? Y squared. Therefore that equals 1 too, and our t is gone. Got it. And what do we notice about that? That is the equation of an ellipse. Standard form for an ellipse is x squared over a squared, or this is for centered at 0, 0. So an ellipse with a center 0, 0 is x squared over a squared plus y squared over b squared equals 1. And a and b are your what's called your directrix. So a, this is a, and this is b. Does it check out with what we got? What do we get for A? 2. Does it check out? Yep. And what do we get for B? 1. It works. Okay. So we look at this and we say, oh, it goes out. The x directrix is 2, meaning half the distance across this way is 2, and then the y directrix is 1. So in some cases, like with linear and maybe quadratic, you solve the x equation for t and you plugged it into y, like we saw earlier. But when you're dealing with sine and cosine, you don't want to do that. You want to use this technique of this is called the Pythagorean identity. The Pythagorean identity is what you want to use when you've got one of your coordinates is sine, the other is cosine. Okay, new example. Other way. Here's the equation of an ellipse. Write it in parametric form.
First one's 16y squared.
X. No, just kidding. This one, yeah, that's X, this is Y. Okay, write it in parametric form. You need to use a little ingenuity here, not much, just takes a little ingenuity. Of course, you're applying this. You got to see how this applies. See if you can do it. Is your theta going to be t? No. How can I give you a hint? Let's see. So you got to get sine and cosine. Don't worry about theta. You got to think about sine and cosine. So you got to get sine and cosine into this so that it matches this. Okay? That it matches this. So how are you going to get sine and cosine involved so that it is consistent with this? We need something squared plus something squared equals 1. That's how we start. What do we got squared? What's squared? We need something squared. What is it? 4x squared. And then something else squared. Y over. Now we're ready to bring sine and cosine into it. Cosine is Cosine of t equals 4x or y over 3. Doesn't matter. Either one. Sine t equals y over 3. That is consistent with cosine and sine squared equals 1. See that? That means that x equals 1/4 cosine t. And y equals 3 sine t. How many got it before I did it? Really? Oh, good. Awesome. It's not irrelevant. It's just what this function was. Just because there was a pi here, there's no... Yeah, you could... Okay, so you could put a pi t if you wanted. You could put 20 pi t in there. As long as it's the same argument. Yeah, so as long as what you're putting into cosine is the same for both sine and cosine, then it's fine. All right, now we could have also done... Yeah.
Does it matter if sine is with y or
Right.
x?
That's what I was going to say. So sine, now let's do sine t equals 4x and cosine t equals y over 3. And then x would be 1/4 sine t. And y would be 3 cosine t. Okay. Different function or same function? So here's function 1, function 2. Different or the same? Different function, but it should give the same points. Let's see it. Okay, let's see it. Okay, so when you come to my office hours, I'm not going to pack up and just walk away on you when I'm talking to you, or when you're talking to me. So if you need to go somewhere, that's cool. Where is that? Did I title it? All right, we don't have time, but I want to try to build it. But here's what it is. So I put in the first one, x is 1/4 sine t, y is 3 cosine t, and the second one in blue, x is 1/4 cosine t, and then 3 sine t. They both give that same set of points. But what happens is, when t equals 0, for that first one, you get this point 0, 3. And when t equals pi over 2, you get this point 1/4 0. Then for the second one, when you put in t equals 0, you get 1/4 0. And then when you put in t equals pi over 2, you get 0, 3. So not only do they start at different points when t equals 0, but they trace out the curve in different directions. So the red one traces it out clockwise, and then the blue one traces it out counterclockwise. But they start at different points, 0, underscoring that it's different functions, right? Totally different functions that give you the same set of points. And so that's one thing with parametric functions. There's like a million ways to write the same set of points with different sets of parametric functions. Okay, so I will see you Wednesday.